Hello, everyone. My name is Raul Quintero, and today I will talk about an algorithm that generates automatically equations that are important in quantum chemistry. So this algorithm has been made in Mathematica. So the outline of this presentation, first, I will start with quantum chemistry background. So I will introduce some quantum mechanics concepts and also quantum chemistry concepts. And then with this background, we will discuss about the main subject, that is the coupled cluster equation and equation of motion coupled cluster. So I will explain why these equations are important and why do we need to generate them automatically. And then I will present the algorithm in an interactive way. I mean, we will change from LaTeX to Mathematica to see how the algorithm works. So starting with the quantum chemistry background. So what is quantum chemistry? According to ChatGPT, is a branch of chemistry that uses the principle of quantum mechanics to understand and predict the behavior of atoms and molecules. And according to Wikipedia, is the branch of physical chemistry focused on the application of quantum mechanics to chemical systems. So yeah, it's basically quantum mechanics applied to chemical problems. So which kind of chemical problems? So here I have 3 examples. So we can understand chemical reaction. So in this example, in the y-axis, we have the energy, and in the x-axis, we have the reaction progress. So at the beginning of the reaction, we will have 2 separated products, A and B, and the addition of both will be a given energy. So then when they start interacting, they will form a transition state higher in energy. And finally, they will bond. So those elements are bounded will form a compound that is stable with respect to the transition state. Another important use of quantum chemistry is the drug design. Whenever a drug is designed, we need to target a protein, an enzyme, or something in our organism. So in this example, I'm showing in this orange circle is the enzyme, and this blue dot is the drug. So we can model the interaction energy between both. So it actually helps to optimize the drug candidates. So if we have many candidates, we can select the one with the minimum energy because they will interact. They will interact more strongly, and the drug will be more efficient. And the third application is spectroscopy. So spectroscopy is basically the study of the interaction of light and matter. So regarding our subject, this is more related. So in this example, I'm showing an emission spectra. Each of these lines represents a transition energy from a higher energy state to a lower energy state. So with respect to these 3 examples, we see that we have something in common, is that we're measuring the energy somehow. So how do we obtain those energy? So we do it through the Schrödinger equation. Sorry for that. Yeah, we do it through the electronic Schrödinger equation. First of all, what electronic? Because atom and molecules are made out of electrons, so the electrons define their behavior. So the electronic Schrödinger equation describes the behavior of electrons and their wave functions. So in this equation, on the right-hand side, first we have the Hamiltonian that is composed by F, that is also called Fock operator, and B is the electron-electron operator. F will contain the interaction between electron and the nucleus, also the kinetic energy of the electrons, and also the electron within mean field. And B will contain just interaction between electrons. F is also called one-body term, and B two-body term. Psi is the wave function, is what we want to obtain, and E is the energy of the system. So this is an eigenvalue equation. So when we solve it, we obtain this wave function and the energy. So we start with a Hamiltonian, is what we propose in this equation, and then make the Hamiltonian acting on the wave function to solve this equation. Another key concept in quantum mechanics is the quantization of energy. So here I'm showing again the emission spectra. So for this emission spectra, imagine we have a gas phase atom. So if we apply some current, the atoms will emit light. So here we are measuring this light emitted for the atom, and each one of these lines correspond the transition from a photon from a higher energy state to the lower one. So yeah, so each one of these energy states will correspond to a different wave function. But as I mentioned before, we are working with electrons. So what are the rules that electrons must follow? So they follow something that we call Pauli's crucial principle, that says that no two electrons in the same atom can have identical values for all 4 of their quantum numbers. So yeah, in the right-hand side, we have this image with 2 electrons with the same energy but different spin. So if we have 2 electrons with the same energy but with the same spin, it's not possible. And for simplicity, we'll represent the 2 electrons with different spin just with dots. But since we have just 2 spins, we cannot have more than 2 electrons for a given energy. So another important concept in quantum chemistry is the electronic configurations. So basically, the electronic configuration is the distribution of electrons in different orbitals. In the right-hand side, I'm just depicting, this is not how an atom looks like, I'm just depicting an atom. And 2 electrons are occupying each of the more internal orbitals. So in this case, we have 5 orbitals and 6 electrons. So a simpler way to depict this image is by just using these orbital energies and electrons. So we have a simple image. And in this is the ground state configuration, and it is also called the reference configuration, where all the electrons are in the lower orbital energies. So some notation, the electrons that are occupying the lower energy levels are called occupied states. And the unoccupied orbital energies are called virtual states. So I will mention that, so it's important to have that in mind. So, but we can also represent different states. So again, if we start from a ground state configuration, we can perform jumps of these electrons. For example, we can make this electron in the level 3 jump to level 4, and from the level 1 to level 5. So when we are doing this single jump, we say that we are obtaining single state configurations. And again, if we start again with our ground state configuration and we perform 2 jumps simultaneously, we are now talking about double excited state configurations. So here I'm representing some of them. of course, we have all the possibilities of 2 jumps. But also, if we perform a jump of 3 electrons simultaneously, we obtain triple excited state configurations. So how do we represent those ground state configurations mathematically? So consider again the ground state. So if we number the positions in the orbital energies as follows: 1, 2, 3, 4, 5, 6. We can say that we are creating in an empty space. It's not empty space, it's physical vacuum, that is just the orbital energies, that we are creating electrons. So for example, here I'm filling this space first with electron 1 and electron 2 that are occupying the lowest orbital energy. Then 3 and 4, that is the second one, and then 5 and 6. So in this way, we are representing this configuration. So this way of representing this is called second quantization. But it's also important to notice that each one of this number is an operator. And whenever the operators contain a dagger, that means that they are creating electrons in the vacuum. So really useful short-form notation for this ground state is just by depicting a 0. So in this way, we are also saying that we are in the reference state. So be aware, because it's easy to confuse this reference state with the physical vacuum. This physical vacuum, again, is the absence of electron and just orbital energies. But whenever there is a 0, we have electrons all in the ground state. So in general, we can write a ground state configuration for a given number of electron and orbital energies as follows. Here we are depicting a product of these creation operators upon the physical vacuum. And we can also represent excited state configurations. So for example, if we start again from the ground state configuration, if we want to represent from it an excited state configuration, I need to remove the electron 5 and create the electron 7. So I am depicting that here by putting a 5 without a dagger. That means that it's an annihilation operator, that this 5 without a dagger will annihilate the 5 with the dagger, and we are creating an electron in the 7th position. So we are using this 7 operator. So after this simple operation, we obtain this exact excited state configuration in second quantization. So we need to annihilate one electron and create another in the reference state. So that's the idea behind creating excited state configuration. So again, this formulation is named second quantization. And in general, if we want to write this single excited configuration in general, we can do it by using a pair of creation annihilation operators acting upon the reference state. So here I is annihilating I. So in this way, we obtain this general single state configuration. So another notation note here is that the indexes A, B, and C creates particle in the virtual orbital spaces. And also the indexes I, J, and K remove electrons from occupied orbital energy. So they create something that we call holes. And if they can act as both, because we have examples where they can act as both, we use the indexes P, Q, R. So again, IBC, ABC, we will call them particles. IJ and K, we'll call them holes. Is another shortcut notation that is very useful. But how can we relate this configuration that I have described with the Schrödinger equation? So for that, we need to use a concept within quantum mechanics, that is the quantum superposition, that refer to the capability for a given state to exist in multiple states concurrently. So for that, we will use the Schrödinger cat. This mental experiment consists in a cat inside a box that is dead and alive at the same time. So if we want to build the Schrödinger equation of that, we need to sum the alive cat state and the dead cat state. So also we can see that there is a number multiplying each one of the states. So it numbers just refers how much present is a given state in our wave function. But okay, in our case, we want to represent atom and molecules. So instead of using this cat, we will use the electronic configuration that I already described. So in this example, I'm representing a generic wave function. So these numbers that I will call coefficients are multiplying each one of these configuration states. So actually, when we obtain the Schrödinger equation, what we obtain are those coefficients. So we know how to solve. We know how to obtain the wave function that is by the Schrödinger equation. So let's consider it again. So if we solve this eigenvalue problem, the eigenvectors of this solution will be the different wave functions, and the eigenvalues will be the energy. So in this example, I'm showing that when I'm solving this, the first eigenvector will be the ground state wave function, that its eigenvalue will be the ground state energy. So the first excited wave function, it's over here, and the energy associated with this wave function will be the second energy, and so on and so forth. So actually, there is a method to obtain all this wave function and all of these energies, and it's called full CI, but it's really expensive. So actually, it can just be used for like small molecules or small atoms. But of course, we have, let's say, a more economic way to also obtain all of the wave functions and the energies. This method is called coupled cluster, an equation of motion coupled cluster. So now we can talk about them with the background. So the textbook definition of coupled cluster is that it's a wave function that is built as an exponential parameterization of the reference state. So here the argument of the exponential is the t, and t is a mathematical object that operates in the reference state configuration to generate excited configurations. So this t is also expanded in single excitations, T1, double excitations, T2, triple excitations, T3. So let's take as an example, what does the T2 do to the reference state? So what it does is it creates all the possible double excited state configurations. So we are creating a sum here of all possible second state configurations. So here we have, remember that we have a part of creation and relation, so we are performing two jumps, but we also have something different with respect to CI, that is the amplitudes. So let's say that this so for one given jump, we will have an amplitude. So if we apply the coupled cluster to the Schrödinger equation, we will obtain an expression like this. So here I also multiply by the left this exponential minus t. So whenever this Hamiltonian is enclosed, so here the exponential minus t is multiplied this Hamiltonian, and then we have the exponential t. So if we have this Hamiltonian between these two exponential, we call it similarity transform Hamiltonian. So I will talk about it a little bit later. So how do we solve these equations computationally? So first, we truncate the exponential up to fourth order. And then we truncate the expansion. So in this example, I'm truncating t equal to t1. So I'm obtaining coupled cluster singles. The singles come from single excitation. But if I have t equal to t1 plus t2, will be coupled cluster singles and doubles, and so on and so forth. And we can also have t equal to t2. That will be coupled cluster doubles. And then after this approximation, we need to project the equations. Here I'm projecting the equations in the reference state and also in the single state configuration. So if we have this set of equations, what we're doing with the first equation is obtain the energy. And in the second equations, we will obtain the amplitudes of the single excited state configurations. So these amplitudes will correspond to the single excited state. So in the end, this amplitude will contribute to this energy. So let's say that we will have a correlated energy by these T1s. So we can obtain all the wave functions with this method or with this way of solving them, but it's very expensive. So instead, what we do is just obtain the minimum energy that corresponds to the ground state. So this way of doing it is achievable even for big molecules. So we obtain the ground states, and the ground state is very important in quantum chemistry for a lot of reasons. So yeah, with coupled cluster, we obtain just the ground state energy that is depicted here, but not the excited state. So here you see that I changed the C from the T's that are the amplitudes. So when we solve, we obtain these amplitudes. And when we apply the Hamiltonian to this wave function, we will obtain this correlated energy by these amplitudes. But how do we obtain with coupled cluster the excited state wave functions? So we do it with equation of motion coupled cluster. So after obtaining the solution of coupled cluster, the amplitudes, so the wave functions, we need to define another operator that is our operator. So we also need to truncate this operator. So the order of this operator will be the basis in which we represent the similarity transform Hamiltonian. For example, if I truncate R, if R is equal to R1 and R2, I will just truncate this expansion to 2. So we will have this operator in a basis of S and this. So we will just have 2 by 2 matrix. So we just need to solve this equation to obtain the eigenenergies that are the transition state and the eigenvectors. Now, with the eigenvectors, we can build the excited state wave functions. So, yeah, to summarize this, what we need to obtain first is the orbital energies. We do it with a method that we call Hartree-Fock. And then that we have our reference that is formed by these orbital energies. We can do coupled cluster. In coupled cluster, we select these excitations, we truncate this T to obtain the similar transform Hamiltonian, the ground state energy, and also the ground state wave function. And then we do the equation of motion coupled cluster when we define R to obtain the transition energies and also the excited state energies. But okay, I haven't answered yet. Why do we need to use a program to generate these equations? So I prepare a small example. So this element here will correspond to the 2,1 element of the equation of motion matrix. So the 2 will correspond to D and the 1 will correspond to S. So to simplify everything, we will just consider T equal to T1. So again, following the recipe, if we do the Taylor expansion, we can truncate it here up to third order because fourth order is 0 and 0 order is also 0. So we have this expression. But okay, let's take again the simplest example of this expansion. So then we need to express this block, the block 2,1 in second quantized form. So when we do it, we obtain first these double excited configurations will be this with the strings of second quantization operators, and the H, if you remember, it will be splitted in the F term and in the B term, the 1 electron and 2 electron operators. And then we have the T1, that it will span all the possible single excited state configurations. And then S, that is just a single excited state. So how do we evaluate this element to obtain, for example, results of atom and molecules? So what we use is combinatorics. So for example, here I take the example of the 2 electron terms. So we need to use this formula. And actually this formula fulfills the Pauli exclusion principle. So what we do with this formula is to generate all the possible combinations between the different sets. Since we have 12 operators, if you can count them, in 4 curly brackets, we will obtain 48 combinations. So that's the reason what we are using a computer to generate these equations. But this is even for a computer. I am just giving a really simple term. We have a much more complicated term. So this will become really difficult even for a computer. So we have a smarter way to do it. So yeah, this is another way to define this second energy term. So just what I'm doing here is just form this all possible bar combinations just between the first set of second quantization operators and the last set. If we form all the possible combinations, we obtain just 8 terms. And we can notice that the first 4 terms are really similar up to exchanging of indexes. So indeed, we can just define one. So in this case, I'm define one called IA. So this will be my definition of this first term. So you see, if I exchange the term, I exchange the I from the J, I will obtain this term, the A for B, this term, and the I and the A for J and B, I will obtain this term. So I will need to represent this expression, and the same case for the blue and the green terms. We just need to represent them once together with these equations. So we can say that we have just 3 unique many-body terms or intermediates. So those terms are super important. We base our work in this in those terms. So for the next section, I want to share a mathematical notebook to see practical examples. So yeah, I will start with the general algorithm. So the input will be the cluster operator and equation of motion operator are those that I already described. So in the next step, we transform this cluster operator or equation of motion cluster operators into second quantized form of this equation of motion matrix that I already showed you. And I also obtain the amplitudes from the cluster operators. In the next step, we use as an input this equation of motion matrix in second quantization to obtain the many body term that we saw in the last part. And then we use these intermediates in second quantization. And in this step, is actually the harder one of the algorithm. We do all the possible combinations that I mentioned before, the part combinations. And finally, we need to operate this delta Kronecker in the summation to obtain everything in terms of the amplitudes and the integrals, the 1 and 2 electron integrals that I described at the beginning. So yeah, this is the input. So here I'm using this particle Hall notation. So if I'm using this, it exactly means that I'm having T1 and T2, and in the equation of motion operator, R1 and R2. So it's a bit slow. So yeah, what we are doing here is just saying, okay, we want to work with this matrix 2 by 2 because the equation of motion operator contain R1 and R2. Okay. So then we'll generate the amplitudes and a string. So if I take this the 2-1 block that I already mentioned in the example. So in this step, we are transforming the operators into second quantized form of this matrix. So for example, if we store everything in this variable called strings. So for the one body operator and for the block 2,1, we obtain this string in this second quantized form. You can notice that the indexes are different because we are interested in obtaining like higher orders, like up to quintuples, quadruples. So if I use I, J, K, they start to mess between each other. So it's better this notation is more systematically, but it's more systematical, but it's the same idea. And then what I do is I obtain the many body terms. So I just need to run that. And yeah, what I'm doing here is this expression in terms of these many body terms will be the following, and it's a total because I have everything stored in a list. And we also obtain the many body strings that are those many body terms, but in second quantized form. And I will close that. And then we need to generate all possible word combination. So yeah, this one is taking a bit more because I took a long string just to show. But yeah, here I have already the output. So you can see that whenever we have like a false entry, we already put a null to don't evaluate it again. So yeah, here I'm showing all the possible part combinations that we obtain. So we also have a sign associated to these part combinations. And yeah, we obtain a lot. And yeah, the final step, we generate these many body terms in terms of the integrals and the amplitudes. So yeah, we obtain these equations. So yeah, the algorithm is like this. It's if you are not really familiar with the notation, could be a little bit complicated for the first time. I understand that. So I would run. So yeah, I have examples of the runs. Some examples that I already run. No, I haven't yet. But yeah, let's obtain the couple cluster singles and doubles. So we need to define singles and doubles that correspond to T1 and T2. And the equation of motion operator is not important here, so we define it as 0, 0. So now we are running the calculation. But it's taking a lot because I have a lot of things open here. Let's wait a bit until we obtain the result. Okay, we can wait for the result. And yeah, for the equation of motion coupled cluster, we need to define the two operators, T1, T2, R1, R2. Here I already run the calculations, so we already obtained the expression. So first we obtain the many body term. This is the execution time. I don't know why the other example is taking a lot. It already finished. So yeah, we obtained the coupled cluster equations here. So first we obtain the energy. First we obtain the expression when we project in the single excited state, and then with the double excited state. Yeah, for the equation of motion coupled cluster, we are using these many body terms, and then the expression of the equation of motion. So we see that here we have these many body terms already here. So we need to just define them and define these equations and define both together to obtain the equations. I have actually examples how they should be programmed, and I also have numerical examples. No, sorry, I just wrote the numerical example. So if we want to calculate the excited state and the ground state of helium, we can use this model that is CC-num, that is equation of motion numeric. So we have two electrons, two orbitals. The atom is centered. Here I'm using Cartesian coordinates. And we need to we need to provide with some integrals and also with the methodology that we're using. So yeah, first, as we first obtain the orbital energies. So here are what we call the molecular orbital energies. Then it's doing the couple cluster singles and double equations. So you can see that is iterating until it obtains the minima, the minimal energy of the ground state. And then it starts with couple cluster, equation of motion couple cluster, sorry. And this is the matrix. I'm just printing it. This example is very small. So I have another example that is bigger. But yeah, the eigenvalues that we obtain are the transition energies. So yeah, like actually, so I have a more complicated example that is water molecule. So here it's a little bit bigger, the input, because I need to define the coordinates. So again, I obtain with Hartree-Fock the molecular orbital energies. And then it takes more time for this iteration to obtain the ground state energy of couple cluster singles and doubles. And look, this is the matrix of equation of motion. This time is huge. So yeah, we need to diagonalize this matrix. So yeah, it's very big. So in the end, we obtain all the transition energies. That means we obtain the spectra. And from my side, that's it. Thanks a lot for tuning. So, yeah, thanks.